Welcome to AMS Talks. I'm joined by Rick Bacon, CEO of Aquametrology Systems. Today he'll be talking with us about the technology options available for wastewater treatment in the power industry. Rick, coal-fired power plants generate wastewater from a range of sources that are characterized by high concentrations of heavy metals, including selenium, mercury, and arsenic. There are several different methods to address these. I wonder if you could give us a little more information about those treatment approaches and how they monitor performance to validate that these trace metals are removed.
Sure thing. Thank you, Carter. So the best way to think about it is there's a three-stage process. And the first one is what's called PhysChem, physical chemical treatment, which is then followed by a biotreatment phase, and then in many cases an ultrafiltration phase. And those have been defined as best available technologies, something that we will question later in this conversation, I'm sure. But what's happening in the first phase is that large amounts of chemicals are being added to the wastewater to essentially precipitate the contaminant of concern, quite usually mercury and arsenic. And those sludge is formed, and that toxic sludge is then removed. So that's the physical chemical phase. The biotreatment phase is used for specifically removing nitrates and selenium. And then the water continues for the final phase, which is to remove residuals of mercury that might not have been removed in the first phase. So that's the existing treatment process, sort of simplified greatly. Monitoring is very patchy, to be honest. The control of these systems without monitoring is unpredictable, and particularly the biotreatment phase. There is use of very elementary lagging sensors, but they are unreliable, and they don't actually measure the selenium that's being removed. They measure a proxy indicator, which is a poor indicator. And the more advanced technologies are now incorporating real-time monitoring of the selenium itself to determine that the biotreatment plant is working effectively. So that's the current picture, if you like.
Well, as coal plants work to meet ever tougher water quality standards, what challenges can they expect from these treatment options?
Well, the first phase is essentially the chemicals that are being used are very expensive, but they're non-specific, which means that they will take out a range of contaminants, not all of them a risk, and we'll finally get round to removing the target contaminants, which are mercury. So there is a lot of heavy overdosing, uncontrolled essentially, to achieve that target. So that's one challenge. The other challenge is that the regulations have been recently tightened up to make it much tougher for these treatment systems to reach the limits that have been set for mercury. Mercury is a very toxic contaminant, and the low levels now make it even more difficult for the first phase to remove the mercury. So they've added at the back end of the process the ultrafiltration that I referred to earlier. Ultrafiltration is, if you like, I mean, it's defined as best available technology, but it's the last shot in the locker really currently. Huge problems. The filters get blocked, clogged, very unreliable. So that's the best available technology today, and it's uncontrolled chemical dosing, followed by a unreliable filtration at the end. The biotreatment piece in the middle is generally, if it's controlled tightly with real-time monitoring, is very effective. It's the beginning and the end at the unreliable points.
Well, given the challenges of the existing technologies, what sorts of benefits can coal plants expect from Stannis tin oxide-based approach?
So Stannis tin oxide is an innovative approach. In the first stage, where we're looking at removing arsenic, some of the selenium, in fact, and mercury, it's a very specific treatment process with very accurate dosing to remove these contaminants of concern. And that can be monitored in real time to ensure that's happening, and doses adjusted if necessary. So we're moving away from overdosing in an uncontrolled fashion to something very controlled and specific. And then on the back end, where we have the ultrafiltration, any chrome that does get through to that point, is captured with another Stannis tin oxide filter, which will remove the mercury without any doubt down to levels well below the regulatory limit, parts per trillion. And again, very effective. The two approaches, though, are much, much cheaper and much more reliable, as I've described, than the existing, what's been defined as best available technology. And so what we're proposing here is both a more effective, but also a more effective technologically, as well as a much more cost competitive approach to dealing with these serious contaminants, which are found around many power stations, both in the USA, India, and China.
Well, there's certainly a lot of advantages to Stannis tin oxide, so we look forward to that coming to market quickly.
Well, we're working on it. We're looking at a number of pilots across the USA. We've done a lot of lab work to prove that this works, and now it's a question of rolling it out. So thank you very much.
Thank you for joining us.
You're welcome.